Hi, and welcome to the Chemours Discovery Hub. I'm Chuck Allgood, Technology Leader for Opteon and Freon band refrigerants, and I'm standing here outside our brand new, state-of-the-art, world-class research and development headquarters and laboratories. Today I want to take you on a never-seen look behind the curtain on how refrigerants are made. So we got a lot of people to see and a lot of stops to make, so let's head on inside and get started. Hi, now I'm inside of our Discovery Hub laboratories, and I want to take you on this journey with me along the development of a refrigerant. So we'll start off with some of the early thermodynamic and computer modeling work we do, and then we'll visit some of our laboratories, our analytical laboratory where we look at refrigerant purity and composition. We'll move over to our materials compatibility to see our sealed tube testing capability, where we look at materials compatibility, lubricant interactions, those type of things. Then we'll talk to some of our engineers about some of the basic engineering data that goes into the development of a refrigerant. We'll stop by where we do compressor calorimetry testing, where we can really isolate the thermodynamic performance in a compressor and take away all the system effects, and then move over to our systems testing that we do in environmental chambers, where we closely can control conditions and look at a piece of equipment, how it operates. We'll also talk a little bit about our flammability testing, and then we'll finish up with the ongoing field support once we've developed, commercialized, and launched a product, what we do to make sure you have all the information, technical support, and training to be very successful with your refrigerants. So if you're ready to get started, let's go. So one of the first things we do when developing a refrigerant is identify a target, whether it's the perfect R22 replacement or a low GWP version of something that looks like 507 or 404, or whatever refrigerant product we're trying to develop. We really start with the basic physical, chemical, and thermodynamic properties, things like boiling points, densities, and vapor pressure curves. So I'm going to turn it over to my friend Luke, who does a lot of that work, so he can explain to you exactly what's involved and how we get started on the refrigerant development process.
Hi, I'm Luke Simoni, and I model the thermophysical properties and phase equilibria for our refrigerant products here in the Fluorochemical Technology Group at Chemours. As we all know, the phase out of HFC refrigerants in jurisdictions around the world has driven the industry to find more environmentally friendly alternatives that also do the same job as working fluids. HFOs like Opteon YF can satisfy the global potential requirements and have attractive refrigerant properties as well. While our OEM partners are developing new equipment, retrofits of existing equipment with new low GWP refrigerant fluids are needed at the forefront. Since refrigerants by nature are volatile, we are limited to relatively small molecules, rendering the likelihood of finding a single low GWP molecule with no ozone depletion potential, no toxicity, low flammability, and the exact thermodynamic properties to satisfy the cooling demand of existing systems is very small. So we look to blends of molecules, where we can use the composition of the blend to tailor the properties of the fluid to match those of incumbent refrigerants like 410A. By way of predictive modeling, we can find the right compositions to provide the high and low system pressures, suction and discharge conditions, refrigerant effect, and system efficiency among number of metrics for existing equipment. Further, it's advantageous when azeotropic compositions can be found that satisfy system requirements. Azeotropes are mixtures where the liquid and equilibrium vapor are at the same composition. This is important because these special mixtures behave much like pure components. And this improves heat transfer, can reduce fractionalization and composition drift, say if there's a leak. Using predictive activity coefficient models and equations of state, we predict the existence, composition, and conditions of binary and even multi-component azeotropic blends. In this fashion, we leverage thermodynamic modeling to get to effective refrigerant formulations in less time and direct experimental laboratory expenses where they are most effective. New refrigerant blends must also interact with the compressor's lubricating oil such that the solubility in the oil results in the proper working viscosity to achieve hydrodynamic lubrication. The proper choice of lubricant, too, can be directed with modeling of phase equilibrium and thermophysical properties. While new HFO-containing blends are soluble in typical polyol ester oils, a balance of solubility and the isograde of the oil's viscosity is needed to achieve the working viscosity required at the compressor's conditions of interest. We must also use phase equilibrium modeling to anticipate any regions of immiscibility that may exist between the refrigerant blend and the lubricating oil to ensure that they are not encountered at the working conditions. After all, you want to lubricate your compressor bearings, not wash them. While modeling is an effective tool to direct efforts in a cost-effective manner, it is not a substitute for experiment. It is experimental data, after all, that informs the model. But in turn, the model should be used to inform the experiment. That is, it informs the experimentalist where the most promising work is to be found.
All right, so we're here in one of our refrigerant laboratories with Hugh. Welcome, Hugh. Why don't you introduce yourself and tell us a little bit what goes on here?
Well, hello. My name is Hugh Mentz. I've worked for Chemours for 30 years. My primary job here within the lab is sealed tube testing, where we test thermal stability and decomposition, miscibility, material compatibility, and chemical stability.
Okay, so it sounds like sealed tubes do a lot of work and produce a lot of data for us. I see a bunch of tubes there in the background. Can you walk us through the basic process, Hugh, on
Sure.
what we do with tubes?
For the stability testing, we take carbon steel, copper, and aluminum coupons, clean them, place them within a clean tube. Then I proceed to neck the tube so we can load the refrigeration products or refrigerants into the tube. We also do testing with various oils depending on the matrix that I'm testing. So we can add the oils into the tubes by a long syringe down through the capillary tube. So once the necking's done, we also do compatibility with various gaskets, O-rings, plastics, and elastomers, depending on the matrix.
So if equipment manufacturer was developing a new compressor or a new air conditioner and they had a seal or elastomer or plastic, they want to make sure it doesn't swell or shrink or get brittle. We would work with them
Yes.
testing our new refrigerants with their materials.
Yes. So once we complete that task, then we actually go over to the loader. And we can process up to 8 tubes at a time on the loader. Place the loader or the tube in the loader itself. Pull a vacuum on the tube. Place the tube itself within liquid nitrogen to help cool it down, to bring the refrigerant back to liquid inside the tube and decrease the pressure. And once that's accomplished, then I load the refrigerant through the loader into the tube using the ideal gas law by reducing adding it by pressure into the tube. Then once that's done, then I will take a torch, and because of the liquid nitrogen pulls a vacuum, as I heat it up, it'll draw the glass in itself, and then I'll slowly heat it and then cut it off with the torch, and then proceed on to annealing it to bring the strength back to the glass.
So after you got the refrigerant and any of the materials of interest and the tubes all sealed up, then it goes through some accelerated aging, or
Yes,
what's the next step?
We place it within the aluminum block for safety, and that goes into an oven. We test up to 200°C, and for 14 days. Those 14 days will mimic 30 years runtime in an actual refrigeration system.
So equipment manufacturers and others will have a good sense of how that refrigerant is going to hold up over the lifetime of their equipment.
Of their equipment, yes. And then once the 14 days is up, I will pull them out, do a visual inspection and observations on the elastomers or metal and how they reacted. And then from there, I will take them down to analytical, where they will actually open them up and analyze the refrigerant
So
decomposition.
So the analytical will look at the fluoride or chloride, the breakdown of the refrigerant. And what are some of the measurements on the actual materials that you measure? Swell, that kind of stuff?
Yeah, on compatibility wise, we do linear swell, weight, thickness, width, and denier or hardness on the material before and after, and then also a post 24 coming out of the oven, and make note of the changes during those times.
Great. Well, thanks so much, Hugh. Appreciate it. I know it's a very complicated and intricate process. It takes a lot of skill and training, and you've been doing it for many years. It's really one of the reasons why we're able to develop such great new refrigerants is the history and the learnings and the basic information that comes out of these tests that we see in the laboratory. So appreciate your time.
Thank you.
Okay, so we're out here with Ryan, one of our chemists here at our Chemours laboratory. Well, welcome, Ryan. Please introduce yourself and tell us what goes on in here.
I'm Ryan Coombs. I'm an analytical chemist here for the Fluorochemical Technical Service Lab. We basically handle all the day-to-day analytical testing for our products that are on the application side, and I'd love to give you guys a tour.
Let's go.
So we do have a couple labs. This is the main one though. Against the wall back here is where most of our wet chemistry is done. So we have a couple Carl Fischers here. These are used for determining water moisture and percent water in samples. We have in the far hood here is where we can analyze our acid and acidity numbers for our samples. We do have a IR instrument here, which can, just another helpful tool to determine what's inside some of our refrigerants. Just on the other side of this, we have our ion chromatography instrument, or IC, similar to GC, except for it uses liquid. And then some of our main instruments here are GCMSs, or gas chromatographs. These are used specifically for testing blends, testing refrigerants, understanding percentage compositions, unknowns, impurities, and things like that. This is a typical refrigerant sampling bag. We blow the refrigerant in here, and it gives us an easy way to inject it into our GC. Disclaimer, this is a standard that is made with about 20 or 30 impurities in here. So let's just do an injection. So we'll quickly follow the path of the molecule here. After it gets injected, it goes through an inlet that's heated up real hot. That'll put everything into a vapor. It then goes through a column, a capillary column. This column is made of material that can interact with the refrigerants. And so different refrigerants will interact with the material differently. And what that does is it kind of slows some down and lets other ones kind of pass through faster. And essentially what it's doing is it's separating out the impurities. So as they kind of make their way along the column here, they'll then enter the detector. This is a mass spec. And from there, they'll go onto the screen and they'll come up as peaks at different times, depending on how they kind of reacted with the column. So again, molecules react differently with the column, so they'll kind of come out at different times on the detector. Okay, so this is in live time here as the peaks come up the column and hit the detector. They get put on the screen here, this graph as peaks. So this is, just to orientate you, this is kind of normalized area counts and then time. So essentially the retention time, what time the peak comes off the column. And each one of these peaks right here is an impurity. This large one here is the pure refrigerant, and these smaller ones here are all the impurities. So you can see the columns separated them nicely here. You're getting nice separations, and this enables us to identify them a lot easier. Okay, so that was the acquisition software. We've now switched over to the quantitation software. So this is where we can identify which peak is what. So I'm gonna zoom in here on this 10-minute peak right here. What we can do is we can do a cross check of it, and on the bottom here, it gives us what we call a fragmentation pattern. So that is essentially a molecule's fingerprint, and each refrigerant may have similar fragmentation patterns or similar fingerprints, but each one is unique into itself, and because of that, we are able to identify what impurity is what based off of a whole library of these in our system. So we're just going to zoom in here on 10, and then we can, and you can see here on top here is what the data we got from our sample, and then underneath of it is our library match, and you can see they line up almost perfectly, perfect match here. This match gives us a quality match of 90%, which is excellent, and that's how we can be confident of what it is. And each peak does it. You can see this peak has now a completely different fragmentation pattern, but the same result. Very good match on top, and with that, this one's 87%, so we're fairly confident of what
so
these
you can know
are.
exactly what those impurities
Correct,
are.
correct.
And identify them, whether this comes from a sample in the field or whatnot.
Correct. Yep. And we can be fairly confident based on these matches, even on unknowns that come in, and they may not have a library match perfect, but main lines here, large lines that match up perfectly, gives us a pretty good indication of what is what.
Great. So let me ask you one last question about the GC. I know in this case the sample was a main refrigerant with a bunch of very low concentration trace impurities, and you can kind of measure the amount of those impurities, but say it was a refrigerant blend with 3 main components, something like 407. You can also use this to measure the amount of those and make sure that the blend is in the proper proportions?
Absolutely. So we're able to measure the impurities on this detector because the mass spec is so sensitive. For blends that we're looking for just composition, percentage composition, we'll use kind of like a less sensitive detector where it's easier for us to calibrate. It'll give us 3 nice peaks and from there we'll be able to get a better percentage compositional number rather than, and then what we do is we kind of ignore the impurities because they're just so low.
Right, they're less than 1%. So for percent composition analysis, we just focus on the main components.
Correct. Yep.
All right, well, thanks so much, Ryan. We appreciate you taking a little time to show us the analytical lab and how we use it in developing refrigerants here. And if anybody has any questions or any needs, we'll certainly get them back to you. Anything else to add? Or?
That's it. I think we got it.
Thanks so much.
Yeah.
So somewhere in the middle of the timeline between we first start the basic research and discovery of a new refrigerant and it's commercialized and you can buy it in a wholesale supplier near you, we go through the process of an ASHRAE submission. That's where we submit data and information to ASHRAE Standard 34 committee and get a number assigned. That's where the R407 numbers, the R449, those are all assigned by going through the ASHRAE Standard 34 process. Two important parts of the data that need to be submitted for that process have to do one with the toxicity and one with the flammability. So we want to hear from our toxicologist here to talk a little bit about the toxicology science and data that's needed to assure that we have safe, good refrigerants when we come out the end of the development cycle.
Hi, my name is Christine Glatt, and I'm a senior toxicologist at the Chemours company. I'd like to talk to you briefly about why toxicology is so important in the refrigerant product development process at Chemours. What toxicology does is it ensures that the products that you use are safe to you, are safe to your customers, and are safe to the planet. Our toxicology team is fully integrated into the entire process of product development at Chemours, from research and development all the way through full commercialization. And what this does is that it ensures that product safety is embedded in all of the decisions and actions that take place through this product development process. Safety is critical to the sustainability of our products at Chemours, and most importantly, in retaining your trust as our customers. Toxicology is the study of the adverse effects that chemicals and agents play on living organisms. So we do many things to help us understand what those adverse effects are. We use various protocols that have been scientifically validated, they're robust, and they're internationally accepted. And very importantly, consider animal welfare in their design. Our team designs very tiered strategies that start with computational modeling, which means that we use computer simulations and models to understand the toxicity, through to in vitro models, which include cell-based systems or in vitro, like I mentioned, as well as whole body or in vivo animal models to understand and characterize the toxicity of a substance. What's also important to understand and characterize the toxicity of a substance is to look at various levels of exposure, durations of exposure, and routes of exposure. So for example, various durations of exposure might include acute or short-term, single 1-hour inhalation exposures or single oral dosing, through to subacute or subchronic, which means 28 or 90-day exposures, all the way through to exposures that simulate a lifetime of a human exposure. Various endpoints are evaluated in these studies. They include things such as clinical observations, central nervous system effects, reproductive effects, endocrine effects, developmental effects, whole tissue and organ histopathology, effects on DNA, and also effects on cancer. All of these taken together are used to characterize the critical hazards that a substance has on a living organism. They support the international chemical regulatory submissions, and then together with regulators and third-party body experts, we use this information along with the information that we have on exposure to the humans and environments that are exposed to the substances to create a risk assessment so that we can ensure that workers and the general public are safe in using our products. Other downstream uses of toxicology data include things such as community and workplace exposure limits, such as ATELs, and occupational exposure limits, such as wheels and TLVs. Other things include classification and labeling for hazard communication, as well as health-based codes and standards that are used by ASHRAE and ISO. So the benefits to you in toxicology testing. Well, I would think that the number one benefit to you from a Chemours product is that you have peace of mind. Peace of mind that the products that you and your customers are using are safe for your health and safe for the environment. As the father or founder, I should say, of modern toxicology once said, and his name is Paracelsus, solely the dose determines that a thing is not a poison. What he means by this is that all things at some concentration or exposure are poisonous, and that at other exposures or concentrations are not poisonous. It is our job as toxicologists to identify what that level of safe exposure is. Our passion at Chemours is safety, and delivering sustainable products that meet this criteria personally makes my job that much more satisfying. So in closing, where you can find information on the safety of our products, the safety data sheet or SDS, and on the websites of the European Chemical Agency or the National Library of Medicine. Thank you so much for listening.
Okay, so we're here with Patrick Coughlin at the Chemours Discovery Hub. It's our R&D center where all our development and testing work for Opteon and Freon refrigerants goes on. And Patrick runs our flammability testing facility. And so I've asked him to talk a little bit about one of the more basic flammability tests in the refrigerants industry, which basically leads to how refrigerants get classified when it comes to flammability to the standard. So Patrick, can you kind of describe the apparatus here that we're going to look at?
Certainly. Thank you, Chuck.
And the test, too? Sorry.
Certainly. The test that we run here to determine the upper and lower flammability limits of a refrigerant and air is based on the ASTM E681. At its heart, what we use is a 12-liter flask and a sample. The sample can be either a pure refrigerant or a blend of refrigerants. What will be done is we will slowly introduce the sample from a liquid composition and expand it into a suitable container, i.e. this flask, up to a desired concentration in air. In this instance, 1, 2, 3, 4, 5%, etc. The idea being that we're trying to find any instance in that air where this mixture suddenly becomes flammable. Once the sample is flown in, we of course introduce air. This test method can be used for both ASHRAE applications or ISO applications, the difference being whether it's moist air or dry reconstituted air. In both instances, a substance is considered flammable only if it ends up having a degree of arc over 90 degrees from its point of ignition. If we ignite it down here, the flame must travel up and then expand out to be 90 degrees. Anything over 90 degrees is considered flammable. At that point, we would either consider it the LFL, or the lower flammable limit, or the upper flammable limit. However, if it happened to be less than 90, this would be considered non-flammable. The reason being that in a real world environment, that flame would no longer be able to continue to propagate. Anything above 90, and it would.
Thanks for that description. I think, can we go down to the lab and take a look at the actual apparatus as it is in real life at this point?
Absolutely.
All right. So as part of the ASHRAE Standard process to get an ASHRAE designation and number, the ASHRAE designation is A1, B1, A or B being the toxicity number, and then 1, 2, 2L, or 3 being the flammability characteristic. So 1 being essentially non-flammable or no flame propagation. 3, that includes things like hydrocarbons, propane, things that are highly flammable or explosive. Then there's the 2 or the 2L that's in the middle. The 2L are sometimes referred to as mildly flammable. But getting back to the standard, we not only have to show the proper classification testing for the refrigerant as it's formulated as we put it in the jug, but also if it leaks or can change composition, we have to understand what levels, if it's multi-component, the flammable components are going up or down to assure that it's safe and meets that flammability classification under any type of use scenarios. So that involves 2 of our laboratories. We've seen one, our analytical laboratory, where we can do these leak and formulation scenarios and verify what the composition ends up being, and then 2, our flammability testing of those worst case mixtures. So you see how a couple of our laboratories contribute to work together in order to get the refrigerant assigned an ASHRAE number and a safety classification. So I'm here with one of our Chemours engineers who works at the Discovery Hub, Jethro, and he's going to take us through some of the refrigeration testing that goes into developing a refrigerant, notably the compressor calorimeter and our systems lab. So welcome, Jethro. How about you introduce yourself and tell us a little bit what goes on in the lab, and then we'll take a walk inside.
All right, my name is Jethro Medina. I've been with Chemours now for about 4 years, working in the Refrigerants Testing Center. I have a background in chemical engineering, and I kind of oversee the day-to-day activities in the refrigerants testing labs. And what we will be seeing today are 2 pieces of equipment that are critical for product development for refrigerants. One is the compressor calorimeter, and the second is a set of environmental testing chambers. So what we have here is a compressor calorimeter, and it is used for the compressor evaluation of a variety of different applications in the HVAC industry. And it allows for a quick screening of multiple refrigerants for these different types of applications. And how it fits into the developmental process of refrigerants is that the compressor takes up a lot of the energy consumption of a refrigeration system. And being able to optimize or minimize the energy consumption of the compressor when developing a new fluid is very important for manufacturers of the fluids as well as the compressors. The compressor calorimeter consists of the compressor chamber over here, and this allows us to interchange the compressor depending on what application we're aiming to test for. In addition to the compressor, we have a variety of temperature sensors, the power meter consumption for the compressor itself, as well as discharge and suction pressure control. And how a typical test works is we decide on a condition. So suppose we're testing air conditioning. We'll take a standard that will provide us an evaporator and a condenser temperature to aim for an air conditioning application. We could then adjust the suction and discharge pressure to adjust for the temperatures that we're aiming for, and then allow the calorimeter to sit steady for about an hour to ensure that the controls are working properly and we're maintaining those conditions that we're aiming for. After the hour has passed, we will then take a 5-minute snapshot of all the temperatures, and particularly the energy consumption of the compressor as well as the cooling capacity of the fluid. And we could take those two values, the cooling capacity and the compressor power consumption, and evaluate that at different refrigerants as well as different compressors. So that's the compressor calorimeter and how it fits into the development of refrigerants. And now we are inside the environmental chambers. We just saw a shot of the indoor chamber. We are in what is typically considered the outdoor chamber. And the types of equipment we test in here consist of residential and commercial air conditioners and heat pumps. Any equipment that will require the use of an outdoor and an indoor condition is what we've been testing thus far. So the chambers themselves, they provide very accurate temperature and humidity control, which is very important for modeling or for setting up the conditions you would typically see for different climate conditions depending on where you are in the world. So right now we actually have a residential air conditioner in the system. And the way this would work is we would set this chamber to an outdoor condition of sometime in the summer, let's say 95 degrees or so. Then the indoor chamber will be set to your typical in-home condition, maybe around 70 Fahrenheit. The compressor is actually located in this outdoor unit here, and the fluid will move from the compressor all the way over to the adjacent chamber, where it's going to enter some duct work that will kind of model what you would see in your house. And as the air will pass over the evaporator coils with that fluid in there, the cooler air will now be dispersed throughout the chamber. And that's sort of an example of how we use both chambers together. And again, the chambers provide very tight temperature and humidity control, so we could specify that to whatever climate condition we are looking for. And that sort of summarizes what we do in terms of testing in the environmental chambers.
Hey, I think it's as good a time as any to take a little detour from our product development journey and talk a little bit about the manufacturing of our refrigerants. We have a lot of dedicated and really expert engineers that design and build and operate our manufacturing assets. For instance, we recently broke ground on the world's largest HFO facility located in Corpus Christi, Texas, where we make the building block, the foundation of all of our Opteon product line. And these are just as important. So as our team is working to understand all the science and engineering and data to develop the best refrigerant products and define those, we also need to invest in state-of-the-art manufacturing facilities so we can make the appropriate quantities and the best quality, and then move it into packaging and then distribution, so that when we identify a great refrigerant product, that it's available on the shelf in a location near you, so you can use it to delight your customers as well. So always want to give a nod out to that. They don't typically show up in the spotlight too often, especially in the industry things, but rest assured they're behind the scenes making us all successful in our jobs and delighting our customers with great refrigerants. So we're in the engineering lab here with two of our refrigerant engineers, Dave and Andrew. So welcome, guys. Why don't you take a second, introduce yourself, and tell us what you do and the kind of work you're doing here in the developing of new refrigerants.
Hi, my name is Andrew Pantsula. I'm a technical service engineer with the Chemours company. I've been with the company now for 7 years. Our group is pretty much at the end of the line, where we are working with end users and OEMs to best optimize their systems for new refrigerants. And there's a lot of work that goes into that. Primarily creating any kind of technical literature that you may need, whether it be PT charts, pressure enthalpy diagrams, retrofit guidelines, really any kind of property that you would need on a refrigerant, our engineering group helps create. We also work in the field to help end users with retrofits. So let's say you had a question on how a valve is going to operate with the new refrigerant, or how's the capacity going to change moving from one refrigerant to another in my existing compressor. We help answer all those questions.
Hi, my name is Dave Snyder. I'm a mechanical engineer with Chemours Refrigerants Tech Service Group. I work between research and development, sales and marketing to support our products, both developmental refrigerants and new, for customers such as equipment manufacturers, design firms, refrigerant technicians, as well as single end users to position our products for your needs. I work in the field doing retrofits anywhere from air conditioning systems all the way up to industrial refrigeration, including recent work that I've done at an industrial chemical plant with a flooded chiller. So while we provide a lot of technical assistance through the phone and email, a lot of the information you need can be found directly online at opteon.com, but feel free to reach out to us directly.
Thanks, guys.
Hello everyone, my name is Jamie Hill. For the past 40 plus years, I've worked in the HVACR industry. In the first 30 years of my career, I was a field technician working on equipment ranging from small reach-ins to large industrial flood systems. Currently, I oversee Chemours training, the Tech-to-Tech phone line, and the Tech-to-Tech email service for our Opteon and Freon refrigerants after they've been commercialized and in the field. The types of training we provide are R22 air conditioning retrofits to MO99 or new 22B, supermarket refrigeration from R22, R44A, R507A to Opteon XP40, refrigerant number 449A. Industrial cold storage retrofits also using Opteon XP40. And a new but very important topic, ASHRAE safety classification A2L, lower and sometimes referred to as a mildly flammable refrigerant. In a typical year, we would train thousands, ranging from first year tech school students to an HVACR engineer. Wholesale branches, conferences, trade schools, and industry associations like RSES, ACA, PHCC, and ASHRAE, we have carried out over the years many face-to-face trainings, and yes, we will be doing that type of training again soon. Webinars or recorded training is available online. Please call the Tech-to-Tech phone number at 866-433-8324 or email us at techtotech@chemours.com. For the past 80 plus years, Chemours has been the leader in refrigerant technology. We are always here to support you and your customers and stand behind our products answering your questions. Again, thanks for the support and be safe.
Well, that's about all we have time for today. So I hope this information was helpful. If there's anything you want to hear more about or any of our experts you want to talk to, please reach out to us here at Chemours. I hope this gave you some insight, and the next time you grab a jug of Freon or Opteon, you'll know you're getting a little more than just the refrigerant in the jug, but you're getting a little bit of that science, engineering, expertise, experience, and know-how we've developed over the last 100 years. Be safe and have a great day.